Good evening, ma'am. Happy Teachers' Day, ma'am.
Thank you. Thank you so much, Satsika.
Good evening, ma'am.
Good evening, Marimuthu. So, last class we have been discussing questions from chemical bonding, right? So, this class, as I've told you already, today we'll be discussing questions from thermodynamics. As far as thermodynamics is concerned, it is from physical chemistry. So, definitely we can expect problems from this chapter. So, formulas are very important. Concepts are equally important, but you have to memorize all those formulas. Please make sure you're thorough with the formula. Okay. So, without formula, if you know the concept also, you cannot solve any numerical. So, please make sure you're thorough with the formula. Okay. Fine. So, shall we start the class? Pundamararisi, shall we start the class, Kanna? Okay, fine.
Yes, ma'am.
Okay, Kanna, okay. Is my screen visible? Is my screen visible? Okay. So, first question. A gas expands by 0.5 liter against a constant pressure of 1 atmosphere. Then the work done in calories is dash. They're asking us to calculate the work done, and we have to express that work done in calories. And the data given is we are provided with pressure and change in volume. So we have to know the formula to calculate work done, and from which obviously you can calculate. So what is the formula to calculate work done? What is the formula? Marimuthu, do you know the formula to calculate work done? Tatvatika? Tatvatika?
No, ma'am.
Okay, I'll tell you. Formula to calculate work done is work done can be represented by an alphabet W, which is equal to pressure into change in volume. Okay. Here, generally in work done, a sign is very important. If the work is done by the system, then W should be negative. If the work is done on the system, then W is positive. Okay. What is work is done by the system? For example, I have a cylinder full of gas, and the cylinder is closed with a frictionless piston. Okay, which means piston can be moved very freely without any friction. So inside the cylinder, I have gaseous system. Okay, if the gas expands, then who's doing the work? If the gas expands, the gaseous molecules which are present inside the container is pushing the piston upwards. So work is done by the system. So if the work is done by the system, then it should be expressed as minus W. Okay. Or another scenario is we are pushing this piston downwards. So we are doing the work on the system. If the work is done on the system, then W must be positive. So, as far as this question is concerned, what is the scenario here? The gas is expanding. So work is done by the system or on the system. Here gas is expanding. So work is done by the system or on the system? By
Done
the
by the
system.
system,
So
ma'am.
W has to be negative. So W is equal to minus P delta V. So what is the external pressure? 1 atmosphere. And directly there we are provided with the change in volume. So gas expands by 0.5 liter, which means delta V is 0.5. 0.5 liter. So what is the answer? Minus 0.5 liter atmosphere. But they're asking us to express it in calories. Actually, what is the conversion? Do you know the conversion from 1 liter atmosphere to calories? 1 liter atmosphere is equal to 24 calories. So what will be the answer? 1 liter atmosphere is 24 calories. So we have only 0.5 liter atmosphere. So how much will be the answer? What will be the answer? Half of 24 is
12 minus 12.10.
very good. Yes. So answer is minus 12. Here the answer is option 2. That is minus 12.10. Ritesh, the answer is minus 12.10. We have to read it as 0.10, not 10. Okay. Fine. Very good, Ritesh. So shall we move on to next question? Ritesh, you are from which class?
Ma'am, 11th standard.
11th standard. Do you know thermodynamics, Kana?
Yes, ma'am.
Fine, okay. How about Tony? You're also from 11th standard, right?
Yes, ma'am.
Yes, ma'am.
Okay. You're done with thermodynamics? Do you know the concepts from thermodynamics? How about Marimuthu? You're from 11th or 12th?
11th, ma'am.
So in your school, thermodynamics was taught or yet to study?
No, ma'am, this is done.
Okay, fine. So I hope you should not have any problem with these problems and all. If you have any problem, you just please let me know. I'll help you guys. So now we'll move on to next question. Here we are provided with some data. Nitrogen triple bond nitrogen, hydrogen single bond hydrogen, nitrogen single bond hydrogen. Bond enthalpies are given. What is bond enthalpy? Basically, bond enthalpy is nothing but bond energy. What is bond energy? Amount of energy supplied to break the chemical bond, or amount of energy released when a new chemical bond is formed. Both the things are applicable for bond energy. Both the definition is applicable for bond energy. So bond enthalpy is also called as bond energy. Here we have three types of chemical bonds. One is N triple bond N, another one is hydrogen single bond hydrogen, and nitrogen single bond hydrogen, and we are provided with all the bond energies. Okay, and they're asking us to calculate the enthalpy change for this reaction. What is enthalpy change? How we should represent enthalpy change? If it is change, then we have to represent it in alphabet. I have to use
H.
very good H. So to calculate enthalpy change for the reaction, we know two formula. One is summation of enthalpy change of formation of product minus summation of enthalpy of formation of reactant. This is one formula. So to use this formula, the data must be enthalpy of formation of products and the reactants. But here the given data is different. We are provided with bond energy. So we cannot use this formula. We have another formula to calculate enthalpy of the reaction. So enthalpy of the reaction is equal to bond enthalpies of the reactant minus summation of bond enthalpies of the product. So this is the formula, right? So here we are provided with bond enthalpies. So we can use this formula. So enthalpy of the reaction is equal to, here what is the reactant? Ammonia is my reactant. As far as ammonia is concerned, the structure is N. Nitrogen is my central atom. So the central atom is connected with 3 hydrogen atoms. So in each ammonia, we have 3 nitrogen hydrogen bonds, right? But according to this equation, we have 2 moles of ammonia. So totally, how many nitrogen hydrogen bonds will be there? In one ammonia, we have 3 nitrogen hydrogen bonds. So in 2 moles of ammonia, how many nitrogen hydrogen bonds will be there?
Ma'am, 6.
6. Very good.
Hydrogen.
Very good. So as far as reactant is concerned, we have only ammonia, that too 2 moles of ammonia. So 6 into nitrogen hydrogen bond. That's it. So as far as product is concerned, we have nitrogen and hydrogen molecule. So here we have only one nitrogen molecule. So one nitrogen triple bond plus, because as far as product is concerned, we have to sum the values of product. So we have nitrogen and hydrogen. So nitrogen I've written here. As far as hydrogen is concerned, we have only one hydrogen single bond in one hydrogen molecule, but here we have 3 moles, right? So 3 into hydrogen single bond. That's it. So all the data are provided here. So 6 into hydrogen bond energy is, what is the nitrogen hydrogen bond enthalpy? 391, right? 391 kilojoule per mole minus, what is the bond enthalpy of nitrogen triple bond nitrogen? 945 kilojoule per mole plus 3 into, what is the bond enthalpy of hydrogen single bond? It is 436. So please simplify this and tell me the value, or tell me the enthalpy change for this reaction. And the total unit is kilojoule per mole. See, here there is a typo error. Kilo has to be expressed with small k and not capital K. If you use capital K in science, then that represents Kelvin and not kilo. Here it is a typo error. Okay. So please tell me the answer.
93 kilojoule.
That's it. Very good, Ratish. Do you have any doubt? Shall we move on to next question? Fine. Okay. Okay, great. Third question. This question is a little different. The data are heat of combustion of carbon, hydrogen, methane are given, and here also they're asking us to calculate the change in enthalpy of this reaction. So here also we have to calculate the value of delta H. Usually we'll be having 2 formulas. One is using bond enthalpy, another one is enthalpy of formation of reactant and product. But according to this question, the data is a little different. We are provided with heat of combustion of carbon, hydrogen and methane. So from this data, we have to calculate the enthalpy change of this reaction. So what is the reaction? Formation of methane from carbon and hydrogen. Okay. So here we need not use any formula, but we have to arrange these equations accordingly to come up with this new equation. So we're going to do it step by step. So please listen carefully. So here they've given us the heat of combustion of carbon. What is combustion? What is combustion?
The compound burns with the help of oxygen.
Okay, yes. So combustion is nothing but burning. So we're going to burn something in presence of oxygen. That is called combustion. Here we have carbon, we have hydrogen, and we have methane. So we're going to write the combustion reaction for all these three chemical species. So as far as carbon is concerned, we have to we're going to react it with oxygen. So carbon and oxygen combines together to give carbon dioxide. So this is the combustion process of carbon. And heat of combustion here is, if you combust carbon in presence of oxygen, amount of heat energy released was minus 94. That's it. And what is the second data? Heat of combustion of hydrogen. So hydrogen plus oxygen gives what? Hydrogen plus oxygen gives water molecule, right? So we have to balance this equation. First equation is already balanced, so we need not worry about that. But as for the second equation is concerned, it is not balanced one, right? Left side I have left side I have 2 moles of hydrogen, H2. Right side also hydrogen, it is 2 moles of hydrogen, so it is balanced. But as far as oxygen is concerned, left side I have 2 oxygen, but right side I have only 1 oxygen. So I have to balance this oxygen. So I'm going to write it as half O2. Is that clear? What is the third data? Combustion of methane. CH4 plus O2 gives, what is the product? If you combust or if you burn any hydrocarbon, then we'll end up with carbon dioxide and water, right? So here the products are carbon dioxide and water. Is my reaction balanced? Is my equation balanced? Left side I have 1 carbon, right side also I have 1 carbon. Left side I have 2 oxygen, but right side I have 3 oxygen atoms. As far as hydrogen is concerned, left side I have 4 hydrogen, right side I have only 2 hydrogen. So to balance this hydrogen, I'm going to write 2 here. Now left side I have 4 hydrogen, right side also I have 4 hydrogen. As far as oxygen is concerned, left side I have only 2 oxygen atoms, but right side I have 4 oxygen atoms. So to balance oxygen, I have to write 2 here. Right. Now the equation is balanced. So what is the heat of combustion of methane? It is minus 213. Is that clear? Do you have any doubt? Okay, fine. Now we have written the data in terms of equations. Okay, now we have to arrange all these 3 equations accordingly to come up with this new equation. Okay, so how to come up with this equation? Very simple. First we'll build this equation. Okay, so first the reactant is carbon atom. Okay, in this given equation, where the carbon atom is present? In this first equation. Actually, in our new equation, carbon has to be our reactant. And in this equation also, carbon was the reactant. So no problem. Write that equation as such. So carbon plus oxygen gives carbon dioxide. I didn't do any change to this equation, so we need not do any change to this value also. Okay. Next, our reactant is hydrogen, but we have 2 moles of hydrogen, right? But here we have hydrogen. Hydrogen is my reactant, but we have only 1 mole of hydrogen. We need 2 moles of hydrogen, right? So we have to multiply this equation by 2. So 2 times of H2 plus half into 2 is 1. So 1 mole of oxygen gives 2 moles of water molecule. So throughout we have to multiply it with 2. So we have to multiply this value also with 2. So minus 68 into 2. Next, uh, our reactants are built. Now we have to check for the product. Here I have methane as the product. In this equation I have methane, but methane is in the reactant side. So what we have to do, we have to move the reactants to the right side, right? Since I'm going to write it in the product side, and all the product I'm going to write it in the reactant side. So carbon dioxide plus 2 moles of H2O gives methane plus 2 moles of oxygen. Now I've exchanged all the reactants to product and product to reactants. So accordingly, I have to change this value. If the value is negative, then I have to write it as positive. If the value is positive, then I have to write it in negative. That's it. Now I'm going to add all these three equations. Have to add these equations. We have to cancel the common terms which are present in the reactant and product. So as far as oxygen is concerned, left side I have 2 moles of oxygen. In product side I have 2 moles of oxygen. I'm going to cancel both these oxygen molecule. That's it. How about carbon dioxide? In this equation, I have carbon dioxide in the product. In this equation, I have carbon dioxide as the reactant. I'm going to cancel this. Is there any common term? Water molecule, right? So in second equation, I have water molecule in the product side. In third equation, I have water molecule in the reactant side. I'm going to cancel all those water molecules. That's it. So what are all the remaining terms? In first equation, I have carbon. In second equation, I have 2 moles of hydrogen. And in third equation, I have methane at the product side. That's it. We have built the equation, right? That's it. So just simplify all these values. You'll come up with the value of enthalpy of the reaction. So 94 minus. So here, without using the formula, we have calculated the enthalpy change for the reaction. What is delta U? Generally, what is delta U? If it was delta H, then that is change in enthalpy. If it is delta U, then that is
Internal.
it is also very good. It is an internal energy. So internal energy can be represented with an alphabet U or capital E. Anything in this form. Okay. Delta E or delta U. Both the alphabet represents internal energy, which is a state function. As per find in change in internal energy is equal to which of the works? So for that, you have to know the formula of internal energy. I'm have to create answer. I give 30 seconds. What is the formula of internal energy? You have studied so many formulas, but now
and